Welcome back to graphing the reciprocals of primary trigonometric functions, and this time we are exploring the reciprocal of tan. So the function y equals cotan x. So what you see in here is a graph of y equals tan x. Y equals tan x is characterized by its vertical asymptotes, and the period length is pi radians. So at the x-intercepts of tan, the value of it would be equal to 0. So since cotan x is calculated as 1 over 10, it means that at the x-intercepts of 10, we'll have the cotan x equal to 1 divided by 0, which is undefined. So what that means is that y equals cotan x will display a vertical asymptote at the x-intercepts of 10. So we're going to draw the vertical asymptotes. We're almost there. And one more here. And one last vertical asymptote down here. So next, we will visit the vertical asymptotes of tan. Now remember, the reason why y equals tan theta had a vertical asymptote at the indicated angles is because tan theta, measured as the ratio of y over x for the angles on the in standard position on the Cartesian plane. At angle 90 degrees, the value of x became 0. So at 90 degrees or pi over 2 radians, the value of y became 0. So I'm going to quickly draw the angle in here just so that we can have a better idea. So the angle 90 is standard position from here to here. So the x-coordinate on the terminal arm will be 0. So that made the tan value equal to some number. So in the unit circle, number 1 divided by 0, which is undefined. And that's what created the vertical asymptote on the graph. Now, going back to cotan ratio, knowing that cotan again is 1 over tan x, at the points where tan has the vertical asymptotes, so, or when tan was 1 over 0, cotan will be equal to 0 over 1. So, therefore, we are going to say that the cotan will have a value of 0, which means that the cotan graph will show x-intercepts. So wherever the vertical asymptotes of tan occurred, the cotan will show the x-intercepts. Now, another important point we look at when we are shaping the graph of cotan is the points where tan value was 1. So we know that the tan of angle 45 degrees, this is 45 right here, is equal to 1 because that creates the special triangle 1, 1, root 2, if you remember. And that makes the tan ratio, which is y over x, equal to 1 over 1. So the tan will be equal to 1 at angles as indicated in here. So it will be equal to 1 at pi over 4, for example. And the reciprocal of 1 being equal to 1 would mean that the cotan will also have a value of 1. Similarly, wherever the tan value was negative 1, so negative 1 would be at negative pi over 4. So it would be negative 1 at negative 5 pi over 4, and so on. Then the cotan will have the same value of negative 1. So wherever tan is 1, cotan is 1. Wherever tan is negative 1, cotan is also negative 1. So we'll mark all these points. Now we are going to shape the graph of cotan. This will be fairly easy for cotan because the tan function, as you notice here, is always increasing. So what that tells us for the cotan is that cotan will be calculated as the reciprocal of an increasing value. And we know that the reciprocal of an increasing value will be a decreasing, or will produce a decreasing value, which means that cotan will be decreasing throughout its domain. So imagine that here we have the cotan passing through these 3 points defined by these 2 vertical asymptotes. And we're going to say that the only way to draw cotan then will be this. So going down in value here and going down in value here. Going down again meeting the x-intercept, meeting y equals -1. So going down, down, and all the way down. And again, going down, down, and all the way down, following the vertical asymptote. And this would be the graph of costan x. As you can see, y equals costan x, again, will have the vertical asymptotes at the following points. So x equals -2 pi, -pi, 0, pi, and 2 pi. So what that means is that the vertical asymptotes will happen every pi radians, and the coefficient is the only thing that changes in here. So that's x equals 0, that's pi, and then 2 pi. So generally speaking, we are going to define the vertical asymptotes as appearing to every pi, and we're going to say that x equals n pi, where n is an integer. Now, for the x-intercepts, we're going to say that the x-intercept will intercepts will appear at negative 3 pi over 2, -1 pi over 2, positive 1 pi over 2, positive 3 pi over 2. So every multiple of pi, and what is special about it is that the x-intercepts will be at every pi over 2, but you notice that the coefficient of pi over 2 at every x-intercept will be 1. So 1 pi over 2, 3 pi over 2, -1 pi over 2, -3 pi over 2. So in order to describe an odd integer, if you remember, we have used that strategy. So if n is an integer, then 2n will be an even integer, which means that if you want to make it odd, you add a 1, and 2n plus 1 will be for sure an odd integer. So the x-intercepts will happen at 2n plus 1 times pi over 2, providing that n is, again, an integer. Now, the domain of the costan function will be defined by the asymptote. So we're going to say x is any real number. Obviously, that's because the costan is a solid line, right? So x is any real number, but x cannot have the value that is excluded by the vertical asymptote. So x different than n pi, again, where n is an integer. As for the range, we're going to say that the values of y can be any real number. Now, you also have a small little chart in here that I encourage you to complete in class, just by using the graph that you've built here, and that will add more understanding to the graph of the costan function. So I hope you enjoyed this video, and I hope that this made sense. Thank you very much for watching and learning from me. Bye for now.